All right, our next speaker is Dr. Jayad Hashemi, and then he has a very prestigious and long introduction, so allow me to go through. Jayad is the lecturer of the structural engineering and the deputy director of the Smart Structure Laboratory at Swinburne, and he has more than 8 years of experience in extreme load performance assessment of complex structural through large-scale hybrid simulation in the United States and Australia. And he holds a Bachelor of Science and Master of Science degrees from Sharif University of Technology, Iran, and a PhD from University at Buffalo, the State University of New York, United States. He has received mentoring in the field of hybrid simulation from eminent researchers at world-leading institutions, including the UC Berkeley, University of Buffalo, Stanford University, Lehigh University, and University of Nevada, Reno. And particularly at Swinburne, he has worked closely with professors Riyad Al-Mahdi and Imad Gad and John Wilson to develop Australian first and only hybrid testing facility known as the Multi-Axis Substructure Testing System. Further, he has been involved in several multi-university and industry-linked research projects on extreme load performance assessment of structure, locally and internationally. Let's welcome Dr. Jayad Hashemi.
Hello, everyone. So in today's presentation, I'd like to talk about the substructuring technique in hybrid simulation, and the fact that when we talk about hybrid simulation, we say that we need to partition the structure into experimental and numerical part. But we never say how, or how this actually process is conducted in the lab, and how we should handle that. So, as the question that we had, how we can make sure that the results that we get from this hybrid modeling is as accurate as possible. So in this outline, I would like to talk about the substructuring first, then introduce some substructuring technique that was developed, I was involved in their development, which is model updating, overlapping domain, geographically distributed, and 6DOF mixed mode control. And at the end, I'm going to talk about the development of the MAST and application, some projects on the application of the MAST system. So just think about this simple structure. So let's say that we want to do the hybrid modeling of this one bay frame here. This one bay frame, it's very simple. We have two elements, element 1, element 2. These are cantilever columns. We have plastic hinges at the base, and then they are attached together through a truss element, and we have mass at this node 1 and node 2. So let's say that resources in my lab is essentially limited, so I have only one actuator that I can use, so that's my single actuator, and then just one column, and for cantilever, for the plastic hinge, I use like this mechanism to dissipate energy. So that's my experimental part. So what happens is that we model this part in the computer, and we use this actuator to apply the deformation or displacement on top of this column. Then the actuator also measures the displacement and force and transfer this information back to numerical model. And that happens through OpenFresco, as we discussed in the morning. So in this example, let's first see how we can model the numerical. So on the numerical side, this truss element, let's model it rigidly. So it's like elastic, rigid. It can easily be modeled in the computer. Element 2, again, consists of an elastic element here, but just for the plastic deformation at the base, we can use Bookwen model. It's like an example. It's a hysteretic model that you set some parameters there, like initial stiffness and the degradation of force and displacement, and you can model this plastic deformation here. So this one is also modeled experimentally. As you can see, these are identical. So the structure has the same design, the same material properties, the same geometry at the base, but because we have limited resources in the lab, we can just test one of them, not the other one. And then we subject this to an extreme event. Here we can select an earthquake, which is El Centro, and we want to run the hybrid. On the experimental part, I use this for the plastic hinge. So you can see that there are these steel coupons. There are 4 steel coupons that we have here. And through buckling or yielding, we can simulate a plastic moment rotation. And the reason for simulating this was just to have sacrificial coupons so we can have repetitive testing when we try things. And of course, we have OpenFresco to help us to link these two together. This modeling was done in OpenSea, so we have all the numerical models, the nodes, the elements, the time integration, everything is modeled in the OpenSeas. And then OpenFresco is the middleware to connect this system to the lab. And I'm not going to go through OpenFresco, but the OpenFresco has 4 modules of elements, site, setup, and control. The information are transformed first from a global model to a local model at the element. The job of the experimental element is just to sit within the finite element such that the finite element thinks that the model is complete. So that's one module of the OpenFresco. The second module is that when the displacements are going to be sent to the lab may not be located next to your computer. It might be somewhere else in the world. So we can have experimental site. Next is that the deformations needs to be transformed to the actuator system. So as you can see, we have these axial, lateral, and rotational degree of freedom, but in the lab we have the actuators like this. So we need to do another transformation there to make sure that the actuators move in such a way that we can apply those deformations on top of the element. And finally, we have the experimental control, the XPC target, and all the control stuff that other speakers mentioned about. And essentially, you will end up with this architecture of hybrid simulation. You have the host PC handling the OpenSeas. You have the controller that controls the actuators and reports back the measured forces. And you have the XPC target to link different speeds of operation. Now, that's the result of that hybrid simulation. So if you can look here, you see that the red one, the red hysteretic response, the force displacement hysteretic response is the red one, while the black one is the Bookven model. While if you have a rigid element on top of these both cantilever models, essentially the response that you should get for the plastic hinges should be identical, because the masses are, it's a symmetrical structure. So when it's being excited by earthquake, then the way that the deformation that is applied on both elements should be exactly identical. Therefore, the forces should be identical. But we see that they are different, and that's because of deficiency of the numerical modeling. Now, particularly, we haven't set any stiffness and strength degradation. So you see like there is no degradation of the force and strength. It's always at the capping point. Now, the first, like this question is being asked frequently, and if you remember, Sean also asked from Professor Musallam that what about the other elements? You are testing only one, what about the other elements? And Professor Musallam answered that we have used model updating. So that's essentially a new technique of substructuring technique for hybrid simulation. The way it works is that you have the element that is tested in the lab, but as the element is being tested, you start to learn about its behavior. And while it's being tested, when it yields, you can, at the same time that it yields, you can actually update the other models that are on your numerical side. Those models that are similar, like they have similar material properties, similar geometry, you just don't know how much is the yield, precise yield point to put there. And we always say that in hybrid model, the experimental part is the most critical part. It's the part that is going to be tested first, it's going to be damaged first, and we're going to learn about it. And we can use that wealth of data to update our numerical model. So How can we do that? In order to do that, the model updating has been used extensively in automotive and aerospace engineering. So for example, a cruise control is an online updating model. So while the car is being driven, there is a measurement and sensing system that reports to the computer that this is the current speed, this is the current speed. And that computer model tries to update the car in such a way that the speed matches to the target speed that you set on the car. So that's called a state estimation, and I use two packages for that, the simplex downhill and unscented Kalman filter. They are very famous in automotive and aerospace engineering. And with simplex downhill model, I just updated the two degradation that I didn't use them, but in unscented Kalman filter, I updated 7 parameters to see if I run the simulation, will I be able to get the same hystéric response. And these are the results. So you see that the downhill simplex, the results of numerical and experimental are acceptable, but in unscented Kalman filter is precisely matched. So you can use unscented Kalman filter in online model updating in a way that if you are testing some part of the structure and your structure has a distributed damage, meaning that other parts are also is going to be damaged, you can learn about your experiment and during the test update the assumptions that you've made. And these are the 7 parameters that the unscented Kalman filter has changed. You see like that during the test how the parameters has been changed in such a way that you can get that information or that forces matched with your forces, similar to the cruise control, to match the speed. And this is, again, another example of model updating. You can test one of the isolation here and update the other isolations of this, base isolations of this bridge based on what you learn from this only testing that you're doing here. Of course, this will improve the results a lot, and you don't have to spend the construction cost and just the time of construction in the lab for the entire bridge and all the equipment that you need. So the next substructuring technique that I would like to talk about started from this project. So this project is a shake table project conducted by Dr. Dimitrios Lignas at the University of Buffalo under supervision of Helmut Krovinkler and Andrew Whitaker. So this is a 1:8 scale testing of a steel structure. So the way that the steel structure is modeled is that you have all the gravity on your gravitational framing system, which we call leaning column, and you have a lateral force resisting system, which is either a brace frame or a moment frame or shear wall that holds the structure if there is a lateral push to the gravitational system. And we have rigid links that attaches this gravity system to the moment frame system, which is essentially the diaphragm action. So the objective of this test was just to learn about this moment frame system. As you can see, it was subjected to 5 levels of ground motion: service level, design level, maximum considered level, collapse level, and global instability one. So that's where the structure becomes globally unstable and collapses. So again, you can see that the damages are mostly concentrated in the first story, and then the second story, and gradually it reduced, and the top floor is essentially have very minimal damage. So we wanted to see if through hybrid simulation, we can reproduce this shake table test result. So I would like to show you the collapse global instability of this system when it was tested by shake table. So you can see that in this one, they needed to design this catching mechanism to prevent the structure to collapse over the equipment and shake tables. So you see that testing collapse through shake table is expensive, it's complex, and you need to essentially fabricate the entire thing while you don't learn anything about this. These are all elastic. So, but you have to put them there to generate the inertia forces. So to reproducing that through hybrid simulation, we come up with a model in OpenSeas. We had the moment frame here. We had the gravity frame here. As you can see, they are lumped mass. And we call them leaning column. And that's the equation of motion that was modeled in OpenSeas. The only nonlinear part of this system was just the hinges, the plastic hinges that was explicitly modeled here. Again, they use these sacrificial coupons to make sure that they can have repetitional testing. And they did some cyclic test results, and we just used those cyclic test results without actually the knowledge of shake table. Then the challenge was that, okay, I want to just build 1.5 story in the lab, and the rest I want to do in the computer. Because if I learn about the first story, I have already learned about the second story, third story, and fourth story. So we needed 2 actuators, one actuator here, one actuator there, to apply the inertia forces that are coming from the gravity part. And then we cut the structure at the mid-height of the second floor, because at the inflection points where the bending moments is 0, and so you don't need to control the bending there. It's just the shear forces that is going to be transferred. But we face the challenge. So when you do that, the collapse mechanism that you see here is different than the collapse mechanism that you see there. And the reason for that is that when you introduce the hinge, although the equilibrium is fine, the compatibility is not satisfied. Both sides of the pin can have different angles. But in the real case, although the demand of moment here is 0, you have compatibility of the formation. So how we could actually resolve this? Again, we came up with the overlapping domains. So overlapping means that in conventional hybrid simulation, you have numerical on one side, experimental on the other side. You apply the deformations on the boundary of the experiment, and you measure the resistance. You transfer it back to the numerical part. But then we propose to extend the domain of numerical and experimental over each other. This way, you need to measure the displacement within the domain of numerical and apply it on the boundary of the experimental, and measure the forces within the domain of the experimental and apply it to the boundary of the numerical. So let's see how we can do it. So we extended, instead of 2.5 story, we extended another half a story here, and we built this half a story here. So this is the overlapping domain. We use these actuator A and actuator 2 to apply these, but then the challenge was that how we can measure the axial, shear, and moment forces from the experiment in here, within the domain, because we don't have the actuators anymore to transfer back the forces. And we need the bending, we need the shear, and we need the axial force. So how can we do it? I propose to use the strain gauges and load cells. So because the mid part of the column is elastic, if you use the strain gauges, you can plot the strain, and from the strain you can plot the bending diagram and calculate what is the bending at the top and at the bottom. Or you can use the load cells. So if I place a load cell at the bottom of the column, I have the shear and bending, and I can transform that to the bending and shear at the top. So, but this one, again, posed a challenge, because now the data acquisition system needs to come to the picture. So all the computers should be able to read and write all this information in real time. So we programmed this through a scrambled memory map. So it's a memory shared by data acquisition system, by the controller, by the XPC target, and all these 3 computers can write and read from these memory maps. And therefore, we could bring that strain gauge data into the hybrid simulation. Then we started to test. You see that there was 5 levels of ground motion, and the black dashed lines are the shake table results. These are the hybrid simulation 1.5 story that we did. So that's particularly look at the base shear forces, because that's the important part that controls the deformation. And you see that they are not bad. And this is the design level. And this is the maximum considered earthquake. Maybe I show you collapse. I don't know why. Yep. Oh, that's good. So that's the collapse one. I mean, we got a pretty good match in all these videos. And that's the final global instability of the frame. So then we validated that overlapping domain. And then now that model was a 1 to 8 scale model. So we moved to a half scale model after that of a steel frame. So you can see that we extracted this frame from this building. It's a 3-bay, 4-story frame. And we tried to just model this in the lab. It's a half-scale simulation, hybrid simulation. And then the rest of the moment frame is modeled in the computer. Again, we used the overlapping domain, but the challenge here was that we needed to also apply the axial forces through force control on the setup. And in the overlapping domain, we added another feature for mixed mode control, meaning that you can apply this deformation, you can apply these forces, but this shear and moment were measured from the strain gauges and fed back to the computer. To the computer. So that's the 160% Loma Prieta earthquake of. Let me try one more time. Yep. And that's the 200 percentage. I can show you the 160 one more time. Yep. So these horizontal actuators are MTS actuators applying the displacement, and the vertical ones are Parker actuators applying the forces on the computer. So the good thing about hybrid is that you can take advantages of many equipment, many software. You can model some part of it in Abacus, another lab somewhere else in the world, some actuators here, and OpenSeas is there. Like everything can be then linked together into one model. The next part, we calibrated this moment frame, and then we attached it to a gravity frame to test the response of the gravity frames under the earthquake. And we repeated this test. And the results that we found is that if you consider just the moment frame, the probability of collapse was 1% under the 150% of maximum considered earthquake. If you consider the moment frame with the slab contribution on the hinges, it's just increased to 2.7%. And if you consider the contribution of the gravity frame, we always ignore that. We just say that it's an unstable system, then it just increases to 5.4% of collapse. Then we thought that, okay, now the overlapping domain is developed and it's with mixed mode. Now let's do it geographically distributed. So for this one, we selected this famous experimental test. It's a 4-story steel building tested on shake table E-Defense Japan under 100% Takatori earthquake. So let's see the video. So it has been designed based on Japan codes of practice, but you can see that all these 4 floors remain elastic. So essentially they paid to construct all of that, but all the damage was just on the first floor of the shake table. So when you closely look on this frame, you see that again it's a soft story collapse mechanism. It's a soft story collapse mechanism. So we thought that let's do that 1.5 story one more time of this shake table to see if we can reproduce this. So again, we used the overlapping domain. We used the mixed mode control, but this time we used this part of the structure in Buffalo and the other part in Kyoto, Japan. So that's the video of that test for different ground motions, and again the results were good. So these are the ground motion response, comparing the hybrid simulation and the shake table test for the last two major parts of the ground motion. Okay, but going back to the same experiments on the shake table, just look at the response of this steel column and these two beams, and we are inside that building. So as you can see, if we want the hybrid simulation to be used in collapse assessment, so you see that it's a multi-directional movement. So we have biaxial bending, we have axial forces, we have the boundary from both directions, and then because if an engineer wants us to really simulate this, like how all these beams or columns or the damage states that we see needs to be reproduced by shake table test, by hybrid simulation. So that element is essentially critical, and you saw that the beams, there were no damage. So this requires to do this type of simulation. We need to do, in substructuring technique, we need to control all 6 degrees of freedom. So we have vertical, lateral, longitudinal, biaxial bending, and torsion. And we need to have the capability of doing it in mixed mode, because in those directions that the structure is stiff, you can control the displacement, because this displacement will be so small that it's less than the resolution of the actuators. So we need to actually apply forces. So for this purpose, there is a need to develop 6 DOF facilities for hybrid simulation. And the mass system is one of the rare facilities that has this capability, that you can actually apply multi-directional, time-varying, and highly coupled 6 DOF forces and deformations on top of your experimental element. And the other nice feature is also switched control. So during the test, you can also switch between displacement to force in each of the degree of freedom that you're controlling. So that actually increases the capabilities of hybrid simulation significantly. So I'm not going to cover a lot about the mass system, because we already discussed about it, just to make sure, just to let you know that the capacities are also large, so it can actually fit, is suitable for large scale and full scale testing. So we have 4 vertical actuators, 1 meganewton, and 2 pairs in perpendicular direction, 1 meganewton in each direction. That can be used for both hybrid simulation and quasi-static testing. However, note that the mass system is not the only feature of Smart Structures Lab for hybrid testing. We have the 1 meganewton machine here, which is, we can be connected to the host PC. We have the target PC here that is attached to the mass system, and also to a generic controller that actually can be used for generic actuators. And all 3 computers are on ScramNet. So this means that you can have an experimental element that is tested by the mass, and at the same time by other actuators that you attach to the element. So it's really good and can accommodate different needs of different experiments easily. So at last part of my presentation, I want to just go over a couple of experimental tests that we've conducted here with the mass system and the substructuring of 6 DOF mixed mode control. So the first one was just to assess the performance of a limited ductility RC column under 6 degrees of freedom of testing. We tested that once through quasi-static cyclic testing and once as part of a numerical model in hybrid simulation to see how the results are different. So you see that the applied lateral deformation follows this hexagonal shape, These are the results. So you see, like, there are large cycles of energy dissipation, but again, the vertical forces is controlled in force. So we have applied just the constant force, and the facility is able to control the vertical force in force control and the biaxial bending in displacement control. And that's really rare to see in hybrid simulation. Then we tested the same column, identical, as part of a building. And as you can see, we selected the corner column because it is subjected to overturning moments from both directions. And that actually causes a lot of force oscillations on top of the column. So that makes it really the case for hybrid simulation. Then so this video shows the response of the hybrid testing. The column in the hybrid testing, we use the Imperial Valley earthquake on the 4 levels of ground motion. So the top 2 plots are the building, the global response. The middle one is the axial force oscillation on top of the column. And the 2 bottom one shows the dissipation of the energy in both directions, in X and Y, which is the shear force versus drift. So that's the service level ground motion. And as you can see, when you compare with cyclic, you see that all the energy tends to dissipate only in one side, rather than cyclic, that we go to both sides. This is called the ratcheting behavior. And I think, again, yeah, and you can see that the axial forces, when you assume there is gravity force, in reality, it could go up to 3 times of the gravity force during a ground motion, and even to tension when you are having overturning to the other side of the building. So the column is being subjected to large axial forces, and on the other hand, all the damages, as you can see, is on one side. So comparing these two together, you see that this dissipation of the energy to one side, which is the ratcheting behavior, shows that the column hasn't been damaged much in hybrid simulation, and the quasi-static testing is an overestimation in applying the damage. On the other side, you see that the axial forces in quasi-static is constant, while in hybrid simulation is more. So they are you can select the fact that like quasi-static is like a conservative way, because these two needs to be considered at the same time. So in hybrid simulation, axial force is more risky, but the ratcheting behavior and dissipation in one side shows less damage. So it's hard to assess if you just count on quasi-static testing. So we calculated the risk of collapse, and we found that the results are quite different. And these results of this study was published in ACI Structural Journal, and the experiment was featured on the cover page. Then another application of the mass is on the repairability of the structures. We call that the repairability is the new ductility, meaning that the structures are normally designed to deform a lot and dissipate a lot of energy just to make sure that they don't collapse and we can protect the life of people. But then, like the experience from Christchurch was that you end up with a city that is full of deformed structures, and essentially all of them needs to be demolished and reconstructed again. So now the new kind of strategy for design should be that the structure should be designed in such a way that after extreme events can be repaired. So we use the CFRP to the damage column, to repair the damage column and see that how the performance is as opposed to a brand new column. And this video shows the response of the repaired column now as opposed to the brand new initial column that was tested. So you see that the FRP application on top and the bottom so the repair was in such a way that we we didn't replace the damage reinforcement. So the reinforcement was, we had yielding, rupture, buckling. We just kept it as is, applied mortar, and wrapped it with FRP. So of course, we couldn't get the strength, the sufficient strength, as opposed to the initial one. But the confinement of the FRP increased the ductility of the column a lot. So that's a good outcome. So if you see after large deformation, the hybrid, actually the CFRP can capture the initial column, the response of the initial column. Then we used these results to calibrate a numerical model, and we conducted the fragility analysis one more time, and we found that the CFRP can be used as an alternative for demolition of the buildings, and it shows quite good results, especially when you look at collapse. They are very good. Even FRP1 has a slight improvement, which is good. Here is just reaching to the ultimate capacity. You see that, again, the repaired building is really safe. And here you see that the FRP structure yielded faster, but the reason for that is that we didn't replace the reinforcement. So it's a quite promising strategy for both retrofitting or repair. Another application of hybrid simulation that we had was just for disaster resilient structures. So we have tested square concrete filled tube columns and circular concrete filled tube columns, which are conventional. They are very good because of the fact that the steel provides both longitudinal and transfers reinforcement for the concrete, and the concrete is confined by the steel, so provides larger axial and flexural capacity and delays the buckling of the steel. So this is really good. A lot of capacity, a lot of ductility, very appropriate, but they have never been tested under complex 6 degrees of freedom testing. So we've done some testing there for high seismic regions. They are appropriate. And then a concept was developed, prefabricated steel tube with Monash colleagues, with Dr. Amin Haidarpour, and this test, this column was it's a hybrid column. So you see that it consists of 4 steel tubes on the corner, which have large capacities but limited ductility. But we have also plates that attach these 4 tubes together, which is mild steel and provides sufficient ductility. So that's a pilot test that we conducted on hybrid simulation of this column to see how it performs, and the results are quite promising for lower seismicity regions, and definitely can be used there. So there are a lot needs to be more on that, on the development of the connections, the detailing at the top, and like column-to-column splicing and all that is under investigations currently. And finally, and this demonstration, this time history, after Graham's presentation today, we'll go to the lab and you see that mass system with this displacement time history. And finally, we have tried to expand hybrid simulation to multi-hazard engineering. And as you know, tsunami these days are very important. In the last 2 decades, 33% of total death and 35% of total economic losses of natural disaster has been linked to tsunami. And essentially 6 out of 10 mega cities are at risk of tsunami. So what we want to do is just to have multi-hazard engineering such that, because hybrid simulation gives you this luxury of modeling the dynamic loads in the computer, so you don't need to simulate the dynamic load in the lab. But you can work out under seismic combined with tsunami, what is the boundary forces that this column will need to experience, and you go to the lab and you apply and see if the column can perform. So that's coming in the next 2 months. So that was my presentation, and thank you, and I would be glad to answer any question.
Thank you very much, Jawad, for your nice presentation, very informative. I have a question. I need to know your comment on the accuracy of hybrid simulation. I guess the accuracy of hybrid simulation perhaps highly depends on proper choosing of the critical component. When the structure, of course, is regular and we have a regular loading on the structure, it's not perhaps too difficult to determine the critical vertical component. But what if the structure is irregular and from the beginning we may not have a proper choose of the critical component? During your presentation, you said that during the hybrid simulation, we are able to learn about the behavior of the rest of the structures. But what if during the hybrid simulation we found that the critical member which we choose at the beginning is not the most critical component, and the most critical component is another component which perhaps has not been included in the physical testing? Is there any possibility to rectify the simulation?
Yeah, I think the accuracy of hybrid simulation is something that we should always consider and we should always be aware of. So let me start from this point that when we say dynamic testing of the entire structure is the best case, it's the best case of simulation, but again, there is no guarantee that it produces the results that you see on the field. Because again, in shake table testing, for example, you have the interaction of a structure to the shake table, you have the boundary effects that are not modeled, you're just considering attaching that element or that structure to the shake table. But the foundation is not really representative of the actual scenario. So that's the one side. On the other side, you have pure numerical simulation. So if you didn't have any experimental work, most of the engineers are using just pure finite elements and engineering like a simulation to produce their results. Now, hybrid simulation is just in the middle. And it depends how many of the experimental elements you can involve. And based on your extensive finite element simulation, you can go ahead with hybrid simulation. So if you are very good at your numerical simulation, and you know that the plastic hinges are forming here, you just don't know how is the cyclic behavior, or like you need to learn more about the interaction curves and things like that. And there are also evidence from the real field that it shows that most of the buildings have all the damages in the first story because it has largest base shear. Or for example, if in a base isolation structure, you expect the base isolation to dissipate energy for you and the rest needs to be elastic. So you need, for hybrid simulation, you need to really do a comprehensive finite element model simulation before actually going to conduct the actual test. But then imagine that you are modeling something in computer, but you wish that one of the models that really troubles you could have been experimentally modeled there. And that's where hybrid simulation sits. But if you can accommodate more and larger assemblies of experimental setup, let's say 4 stories I can build in the lab, but I don't have shake table. Then it just improves and improves and improves. So as you move forward toward building more and more elements, your accuracy becomes better and better. But we always need to think that even if we had shake table, the results is not, there is no guarantee that it's 100% what is happening in the lab, in the field.
Thank you.
Yeah. So, Sean, you have?
Just very quickly, can you go a little bit more detail about the model updating procedure you set up? Is it done in OpenSys?
It can be done in OpenSys, but there was a plan that Frank adds this feature to OpenSys, but currently all of these state estimation packages are available in MATLAB easily, because many of the automotive and aerospace people are using MATLAB for that purpose. But yeah, model updating, the idea of model updating first came with Professor El-Nashai, and then it was in a conference. And then after that, many organizations tried to do it, and we were one of the first who could do it. But then after that, it was extensively used in hybrid simulation. So if you look it up, different state estimation, different structures, bridges, base isolations, buildings, everyone essentially is implementing that. Even Professor Musalla mentioned about that blade that is being used. Yeah? Yeah?
In this numerical simulation, say you want to simulate part of the soil structure in FE program and the column itself in a different analytical tool. Is it possible to use like the analytical side to be run along different platforms and the experimental?
Sure. So hybrid testing, I mean, what Sean also mentioned about virtual hybrid simulation is called, traditionally it's called FE coupled simulation. So when you are more comfortable of modeling a wall in ANSYS, but the structural framing doesn't have to be in ANSYS, it can be used, it can be implemented in a more efficient software like OpenSys. Yeah, so these can be linked together, and we are using these before going to the lab for hybrid simulation to make sure that the substructuring technique works fine. But then later, yes, you can have, like I said, you can have one of the subassemblies experimentally. We call the model that actually holds the entire dynamic equation master. And then as you extract elements from that, each one of these are a slave. And each of these models can be modeled in a lab, or it can be modeled in a computer software, and all of this is connected with OpenFresco together. So you can have one wall modeled in ANSYS, one wall modeled in UC Berkeley, one column modeled in our lab here. The computer model could be in Switzerland, and all of these are linked together with OpenFresco. And you can have one single simulation that all of these are at the same time running. So that's the benefit of having hybrid simulation, and it's all, I mean, the coming of hybrid simulation was just all about the cost effectiveness, just because of just small, like simple equipment, but not sacrificing accuracy a lot. Yeah?
So I'm just curious how you pass the signals from one country to another, and how latent can those signals be?
Sure. So we use IT people, and they do it for us. But I think that if you are not running real time, because the only university that I've heard about real time is Lehigh, that they say that they have done real time distributed. But because the testing is a scale time, for example, 20 seconds of an earthquake could take 4 hours in a scale time, you have sufficient time to send the data, but we typically choose those times that are not peak times of using internet. So they're like in midnight or, but yeah.
All over the world, somebody.
Yeah, of course, yeah. But we have delay compensations. So we know that after all these displacements are applied, we wait for all the forces to come back. Once all received, the equation of motion is solved for the next step. It's going to be distributed. Okay, thank you very much. Yeah.
You also have 1 meganewton machine. So
yes.
How effective it is in hybrid simulation? Because it can only provide 1 degree of freedom.
Yeah, so it depends on, like sometimes, like the first example that I showed you is about forming a plastic deformation, like you're testing a connection, and the connection is not under combined action. There is no axial force on that connection. You just want to apply rotation and then see how much bending is there. So even you just need 1 DOF. Essentially, any substructuring that you need 1 DOF to be controlled, you can assign it to 1 actuator to do it for you. So if you're dealing with, and then that machine can be used mostly for proof of concept tests, like the model updating. You want to test if it works or no, or you don't want to go to large and massive construction of all these specimens, and so you need to do some validation checks. So that's also can be used for that.
Okay, and also for the real-time hybrid simulation,
yeah.
One of the slides was showing that only Simulink models can be used.
Yes.
So what is the reason
I can,
access
yeah.
other-
Yeah, so when you want to run hybrid simulation in real time, you have to make sure that your numerical part can be run or can be executed faster than real time. So let's say that you have 20 seconds of ground motion. If I want to model this in my numerical model, and my numerical model takes 20 minutes to run these 20 seconds, of course you can't do it in hybrid simulation. So mostly only mass and damping and some simple material models are modeled. And for that purpose, you don't need a luxury software like ANSYS or Abacus. You can program it in Simulink.
So you only
It's a one
transfer
block.
the mass damping and the stiffness matrices there.
Yes, you can. Yeah, it's an equation of motion. You just say that this is lumped mass, this is lumped damping, and some of my elements are also modeled by linear, no problem. Then you block it, you compile everything into a one block in Simulink. And then Simulink, because it's going to be downloaded to target machine just handles it like in the CPU and can feed the displacement and get the forces back. But I think that what Professor Musallam was showing on the electrical device, he used OpenSeas, but I think they removed the XPC target to remove the delays. I mean, they did a lot of efficiency. Some people even extract some classes from OpenSeas to make sure that it's super efficient and add more CPUs. And then they use directly the commands from OpenSeas to the controller without any middleware or anything else. So that's also some other way of doing it.
Thank you.
Yeah. Okay, thanks very much.
Yes, thank you, Dr. Jayad Hashemi.